Okay, welcome back. In today's lecture, we finally make use of all the machinery we've been developing over the last several lectures concerning the quantum many-body problem, and in particular, the electrostructure problem of quantum chemistry, in order to begin a journey inside molecular physics. So, in principle, our goal is to show how quantum mechanics actually predicts the existence of molecules. And in fact, predicts in, today we will discuss a very simple model, probably a minimalistic model, that explains why, if you take two, for instance, hydrogen atoms, put them sufficiently close to one another, they rather form a unique system, a bound state system, rather than, remaining on themselves. So let's formulate this problem. So we suppose we have two hydrogen atoms with a given nucleus at position Ra, that's the first hydrogen atom, let's call the first hydrogen atom A, and the second hydrogen atom B. And let Ra be in some reference frame the position of the first hydrogen atom, and let there be an electron which we will call which we will label with the index 1, the first electron in our problem. And of course, you can have a distance of this electron from the origin. That was going to be R1. Let me draw it. So let's say it's RA, and I'm going to draw R1. But we are interested in particular in this distance, the distance from the first electron from the center of the proton of the 8th atom. Let's call it R1A. Why is that? Because we know that, this system, this electron is actually bound to the nucleus A into an hydrogen atom, which means that there is a wave function that we call 5A, which involves the distance R1A only. And this is supposed to be the ground state wave function for H atom A. Very well. Now, what does that imply? It implies that if I were to draw a density plot here, denoting with this cloud where I have the largest probability of finding the electron, it will be something like a cloud, which will decay exponentially as R1A becomes large. We have already done these calculations in the context of variational methods. Now, at some distance, which we'll be specifying later, there's a second atom, which we'll refer to as B. I'm sorry. Oops. Second atom B is, let's put the second atom B here. Let RAB be the distance between the center of the proton in A and the center of the proton in B. And let there be a second electron bound to this atom. Let's call it 2. And let's be this R to B. And in principle, I should draw, this is RB. In some reference frame O, which is, of course, completely arbitrary. And as before, I can associate a wave function phi b, which depends on the distance between the electron 2 and the atom and the nucleus p, which is a ground state wave function of the electron 2 in the second H atom. So this is ground state wave functions, which again means that, if I were to draw phi b in this graph, it will be something decay with a distance. Okay, we already know that an electron and a proton, if sufficiently close and with sufficiently small energy and angular momentum, relative angular momentum, like to form a ground state, because the energy of each of these states, quantum states, is lower than the energy of the electron alone in space. In fact, I know that if I take the Hamiltonian for the hydrogen atom, let's call it HA, and I apply phi A, I'm gonna get some energy E naught phi A, where E naught is, roughly speaking, minus 13 point something, let's say minus 13, without being too precise, electron volt. And the same, of course, happens with the second atom. Same energy, because it's the same ground state. It's just shifted. It's another system, identical system. Of course, it will have the same energy. Now, the question we want to ask is what happens when the distance ARAB becomes closer and closer. And clearly, from the physics-based point of view, electron 1 will begin experiencing new interactions, in addition to those that already experiences in the context of his own atom. And in particular, it will begin experiencing the attraction to the second atom, which I will denote as the distance between, which will depend on the distance between the first electron and the B atom. Likewise, the second electron will begin experiencing the attraction of the first nucleus. And the two electrons will begin repelling each other. And so will the two protons. So you see the network of interactions that is there once you get these two atoms closer and closer is in fact much more complex. And the corresponding problem becomes a two-body problem for the electrons. And it's a two-body problem only if you assume that the nuclei can be treated in the adiabatic Born-Oppenheimer approximation. Remember, we are assuming that the mass of the two nuclei is sufficiently large to be able to neglect their dynamics when we consider the ground state of the electronic wave function. So for the sake of this exercise, we will be considering the ground state energy of this system, two electrons in the field of two static charges representing the proton. And we will consider the energy of this ground state as a function of the distance A, R, and B. Now, what do we expect this energy to look like? This is our goal. We want to evaluate this. The energy of the whole system as a function of distance between the centers of the atoms. So how do we expect this energy should look like? Well, basically, it should look like this. When the distance becomes very large, much larger than the typical size of an atom, the energy should be given by twice the ground state energy of each atom. It should not go to zero, because it will go to zero if I take my electrons, strip them off their own atoms, and really let the system explode and be far apart. Every single particle will be far from each other, then clearly the electron will stop experiencing any force, or sorry, in quantum mechanics there's no force, but any interaction with any other electron or any other proton in the system, and the energy will be zero. However, I am assuming that these two electrons are close to their respective nucleus, so they will form an electronic bound state, and therefore, if the two systems are very far, we expect the energy to go to, twice the energy of the hydrogen atom. So that's roughly speaking minus 26 electron volts or something like that. And then what happens if I get close enough? Well, I could imagine two possible scenarios, and these are just speculation for the moment. One possible scenario, which I would call scenario 1, is one in which when I get closer and closer, the clouds of the electron will begin to play a role far before the attraction of the electron with the other proton will set in, and therefore will dominate. And you'll never be able to melt these two atoms together because they will be repelled by the electrostatic repulsion between these forces. So clearly, in this case, there is not going to be any molecule. The two atoms, if you get the atom, if you bunch the atom one against the other with a certain kinetic energy, this is the kinetic energy of the nuclei coming together. So the energy of the two atoms coming together with a certain kinetic energy will eventually hit an inversion point to go back. And no matter where you put yourself in this plane, you will be always driven away from the distance. That's the case in which there's no bound state. But I can imagine a second scenario, which is one in which ultimately if I get them close, then at some point the electrons will like to sit in the vicinity of both nuclei because they enjoy the attraction provided by both, more than they suffer their own repulsion. Well, if so happens, which is a scenario, there will be a bound state, and the characteristic distance will be the size of the H2 molecules. How do I know there is a bound state? If there is a bound state, because the energy of this state will be lower than the energy of the two atoms by themselves. So nature likes to lower the energy, and it will go naturally into that configuration and try to stay there. Okay, so how do we find out? Well, we need to make a model, and we will use a model based on a simple variational, I would say variationally inspired. Why do I call it variationally inspired? Because as we shall see in a moment, I will not involve any, any incremental change of any variational parameter. I will just confront the two scenarios and choose whichever has the lowest energy, which is inspired by the Rits theorem. Okay, so the idea is to use an independent particle model of the type that we discussed in the previous lecture through the Slater determinant. So let's see what it is. The idea is to split the wave function of this system, which is depending on the position of the atoms and their spin, into two parts. A spatial part, which is a function only on the positions, and the spin part, which is only a function of the spins. So this combination, this possibility of factorizing spin and spatial part into two parts comes once again from the observation that the Hamiltonian doesn't contain any term mixing spin and positions. In fact, the Hamiltonian in my system, which I'm going to write here for reference, and the kinetic energy of two electrons, have the Coulomb repulsion, Coulomb attraction of first electron, Coulomb attraction of the second electron with their own atom, the Coulomb attraction between the first electron and the second atom, the nucleus, and the Coulomb attraction between the second electron and the first nucleus, and the repulsion between the two electrons, and the repulsion between the two nucleus, but this is a constant, because we're assuming we are solving this problem. Solving this problem, sorry, apologize, start off. We are solving this problem for fixed nuclear positions. So this is a constant that we can actually disregard it in principle when we solve the Schrödinger equation and put it back in the end when we consider the topology. But as you can see, there's no term involving spin. So it is and in particular, there's no term involving spin and position at the same time because there's no term involving spin. And if you remember from all the discussions we had in the past, anytime the Hamiltonian can be considered as a sum of two parts, each one depending on a subset of variables, then the wave function can be factorized in two parts, each one depending on the corresponding set of variables. We saw that fact several times in this course. So, since this is one of those cases, a trivial case because there's no dependence on the spin at all, I can always factorize the wave functions in positions and spin. I cannot, I cannot assume there is no spin, however, because as we have seen in the previous lectures, the presence of spin has an important impact on the statistics because when you have two electrons in the you can still put two electrons in the same quantum state as long as you use different spin combinations. Very good. So what we know, so let's call this the total Hamiltonian, and let's forget about it. You can always rewind your lectures if you forget the expression. That's my H total. Now, foot. All right. Now, I have to now remember that there is an important constraint on the structure of this wave function, and it has to be completely antisymmetric. Under exchange of electron 1 with electron 2, which simply amounts of exchanging the labels of electron 1 and electron 2. Now, there are many ways in which you can implement this complete antisymmetry. By no means, there is only one. But in this model, we will focus on the simplest model, which is actually physically motivated. But I don't want to, give too much information on why this is the case. Why the following way of realizing the total antisymmetry is important from a physical point of view, because that would require a little bit of discussion of how you sum up angular momentum, which is a topic we did not discuss in this course yet, and probably will not discuss this year. But the possibilities are that, simplest possibility is that each of these functions, phi and k, has its own symmetry. For instance, I could have that this is antisymmetric under exchange of 1 and 2, or this could be symmetric. Likewise, chi could be symmetric under exchange of 1 and 2, or could be symmetric. However, since the product of two symmetric functions is symmetric and the product of two antisymmetric functions is symmetric, we are left with only two possibilities, that either 5 is antisymmetric and chi is symmetric, or 5 is symmetric and chi is antisymmetric. So that if you multiply symmetric times antisymmetric or antisymmetric times symmetric, in both cases you get a complete antisymmetric wave function for the H2. So let's, how do we build antisymmetric wave functions? We know that from this later determinant lecture. So let's say phi antisymmetric is going to be the antisymmetric combination of ground states, single particle wave function. Likewise, the symmetric combination will be having a plus here. Similarly, I can use the same construction that we saw in this later determinant to build an antisymmetric and symmetric combination of wave functions. I can use spin up, spin the particle up being up, then the spin of particle 2 being down, negative, spin of particle 1 being down, spin of particle 2 being up. Or I could put a plus. These are the symmetric antisymmetric combinations we've discussed several times in this course. I can, instead of writing spin of particle 1 and spin of particle 2, using two dependent bracket notation, I can use a unique bracket notation where I label that what I agree from the outset conventionally that the first position is for spin 1 and the second position is for spin 2. So I can get this much more compact notation. Now then once I've defined this, then I have two my variational space in this very simple model has just two possible choices. I have first scenario, the total wave function. I have two possibilities for the total wave function. Possibility 1 is I choosing the antisymmetric and the symmetric, and the possibility 2, I choose the symmetric and the antisymmetric. And I want to emphasize that in both cases, this is a model because I'm assuming that both this and this, well, actually, so most of all, I'm assuming that this is a product of single particle wave functions, which in general should not be. It's only true in some mean field approximation. So I'm doing a model. However, this factorization is not a model because it is actually true that the Hamiltonian doesn't contain any spin. So this part is actually exact. But this is really a model, single particle model. Okay, but maybe models are good enough to get us, maybe they are not very accurate, they don't give us the complete answer, but it might be sufficiently accurate to yield some semi-quantitative or qualitative insight. So how do we find out whichever of these two is the best solution? Which is best? Well, Rits theorem tells us the answer to this question. Rits theorem says that I should evaluate the expectation value of my total Hamiltonian in either state, let's call it E1, and in the second trial state, let's call it E2, and compare them. The one with the least energy would be the best model for my system. Now, fortunately, you can compute these integrals because they are, let's look at the first one, for instance. How would you compute? Now, you would take the integral over dr1a, integral over dr2. So you know better. You would take it in, you would take it. Remember, all distances are calculated with respect to the same reference frame. This is RA, this is RB, this is R1, this is R2, and then you can start building from trigonometry R1A, that's the difference between these vectors. You can build R2B, then you can build R12. You can get all of them from trigonometry if you play around with differences between vectors. For instance, the distance R12 is nothing but the modulus of the vector R1 minus R2. And you can do that for all the distances in this integral. And therefore, let's see how does E1 looks like. E1 looks like the integral over the first electron, integral over the second electron, because the wave function depends on two positions. And then I would take the symmetric combination. I don't remember whether psi1 was the symmetric or the antisymmetric. I think it was the antisymmetric of R1, R2, right? I would take H tot and multiply by phi R1, R2 antisymmetric. Now, this will involve a bunch of derivatives and Coulomb term. And this will be CB4 for explicit definition. So, I mean, I'm not up here to do this calculation. It will take about an hour to do that. And I used to do that in previous versions of this course when I had a little more time, having the possibility of doing the lectures live. However, what happens after you do it? And you combine everything, Coulombic repulsions, the static Coulombic repulsion between the nuclei and these results. Well, you find something different, the following thing. Oh, bad drawer, bad drawer. So remember the scenarios we spoke about. In both cases, you're bound to approach this asymptotic twice as naught. Limit, this is the ground state Born-Oppenheimer energy as a function of RAB, and this is RAB. And this is in the scenario in which the spatial wave function is antisymmetric and the spin wave function is symmetric. This is the so-called, I guess we call it psi1. And this is the scenario where the spatial wave function is symmetric and the spin wave function is antisymmetric, which is what we call psi. So clearly, this is the most realistic scenario. This is our best guess for the ground state. And look, it is bound. It does predict binding. So since the best we could find is already lower than 2 E naught, it means that the right solution will be even lower, and therefore, even more so, there will be a bound state of 2 electrons into the hydrogen atom. Not only this model predicts a fairly decent distance, optimal distance for these 2 atoms, and the typical energy of the 2 atoms. Now, if I look at what is the value, now I think I didn't calculate it at some point. Let me say, I think it's yes. So that's 2.7 angstrom. No, actually 0.7 angstrom. And this is negative, the distance relative to the hydrogen distance is minus 3.5 electron. Now these are predictions that can be matched against experiment, and I'm leaving to you to Google hydrogen molecule and see whether these are good or bad predictions. And remember, we don't expect them to be perfect. We expect it to be okay. Okay, so there we go. We predicted from quantum mechanics using Rits principle and antisymmetric wave function the existence of a hydrogen molecule. Therefore, the existence of molecules, if you want, just as much as it's, for the hydrogen atom, we paved the way to do atomic physics. From the hydrogen molecule, the simplest possible molecule, you see that quantum mechanics predicts the existence of molecules altogether. Okay, that's it for now. Thank you for your attention and see you tomorrow.